Hello, I'm Raymond Hoofs. I'm sorry, first of all, for my voice for this recording. I have a bit of a cold. But I'm from ESA, I work on the Rosetta project. I work in the European Space Astronomy Center in Madrid, from where we operate Rosetta. And I'm going to talk to you about Rosetta, about the mission, and about the planning of the operations. And I will show this through some slides in a presentation. So for the Rosetta mission, let's first discuss why the Rosetta mission is so important. And basically it's a journey to the origins of the solar system. The solar system formed from a big cloud of dust and gas which was contracting together 5 billion years ago. And as it was contracting together, the sun was forming in the middle, and at some point started its nuclear fusion, lightening the whole solar system, but also starting to push dust away, and the planets started forming. So the comets, they remained on the outskirts of the solar system and stay there as, let's say, the original material of which the solar system formed. So by analyzing comets, we are basically looking back in time and looking to the origin of this original dust cloud of which the solar system formed. So we see two belts of comets. There is the Kuiper belt and the further Oort cloud, where there is many comets located. So they are very far away. And sometimes some of these objects get pulled in by the gravity of mainly Jupiter and make a journey towards the sun to then either crash on the sun or fly back out again. Now, if they, on the way out, come close to Jupiter again and Jupiter pulls them another time, we get a so-called Jupiter-class comet, which will have a rotation period around 5 to 6 years, and we can observe those, and then we can build a spacecraft to fly to these kind of comets, and that's what was done for Rosetta. One note about comets in general. I think many of us, you all know the comets from the night sky. Normally in our lives there is a period where there's a bright comet visible and we see them as marvelous objects in the night sky, normally with a long tail, very well visible. They've been an inspiration already from the ancient past because of their beauty in the night sky. Now the comets, when they fly in, some of them crash directly into the sun. Other ones, they pass by the sun very close, like Comet Ison in 2013, which basically disintegrated completely in its passing, and this is very nice shown in a SOHO image of the comet passing the sun. Let me go to the specific comet for Rosetta. It's 67P Churyumov-Gerasimenko. This is discovered by Klim Churyumov and Svetlana Gerasimenko. And this is, like I said, a Jupiter-class orbit with an orbital period about 6.5 years. And this was a good target for Rosetta to go to. For the Rosetta mission profile, the main mission, the Comet mission, started in January 2014 when the spacecraft woke up after a period of hibernation. And the challenge was to analyze the comet as quickly as possible, to be able to find the right landing spots and land the Philae lander on the comet around November 2014. Then after the lander we would fly along with the comet to the perihelion where the comet would be most active and fly out with it again into deep space. So the nominal mission would end December 2015, and we would get an extension to at least July 2016, after which the spacecraft would go so far out together with the comet that the spacecraft cannot be operated anymore. There are many goals. One of them, of course, is to characterize what are comets made of and what is the nucleus of the comet made of. There have already been a number of flybys of comets, but never an orbiting mission, so only a quick snapshot. And we have seen that comets are quite different. Some of them are very strongly evolved, and some of them are least evolved. So, of course, for our lander, it would have been best to have a least evolved comet, so there was a lot of space to land on. But we had to find out when we would arrive at the comet in the summer of 2014. Now the Rosetta spacecraft and the lander itself, let me give a description of that. The Rosetta spacecraft is quite large. The body is about 2.8 by 2 meters, a cube size, but it has very large solar panels, 32 meters width, in order to be able to generate power at the far distances where Rosetta will go. And the launch weight was about 2,900 kilos, which is quite big, and is a lot of fuel for the maneuvering that Rosetta had to do. And it carries 11 scientific instruments on board. Another important thing of the orbiter is the Huygens antenna, which is a steerable antenna, which means we can keep it pointing to Earth while we are observing the comet. Then we have, of course, the lander Philae. It's attached to the Rosetta spacecraft for the travel in deep space. It's about 85 centimeters by 85 centimeters, but when it's deployed, it has the legs out, of course. It's about 100 kilo, and it also has 10 scientific instruments on board. A bit of detail about the scientific instruments. I will not go through all of them, but just give an overview of the most important sets of instruments. There are, of course, the imaging instruments, the cameras, the infrared spectrometers that will take the remote sensing observations of the comet. Then there are a set of instruments that collect dust and analyze the dust. There are instruments that analyze the gas around the comet, of which the gas is made, and the pressure levels of the gases. There is the plasma instruments that check the magnetic field around the comet. There are some very important technical subsystems I want to mention as well. One is the navigation cameras on top of the Rosetta spacecraft, which take pictures of the comet in order to do the orbit determination relative to the actual comet. So by tracking landmarks on the comet, we can very accurately navigate the spacecraft around the comet. The other systems are the star trackers. They take pictures of the stars in order to know the exact attitude of the spacecraft. And they have to deal with the dust environment of the comet, and they were made to do so. So they can work even though there is a lot of dust particles around them that result in false stars. Later in the mission, it became clear that the star tracker performance, because of the dust, is driving how close Rosetta could be to the comet. And actually, because the dust increases as we go closer to the sun, the spacecraft had to go further away from the comet in order to be able to do proper attitude determination with the star trackers. The next overview is from the Philae lander. There I'm not the expert. The Philae lander was operated not directly by our control center, but through dedicated control centers in Germany and France. The Philae lander has several important scientific instruments. One of them is the SIVA camera, which makes panoramic images around the lander. Very important subsystem. Then there were several chemistry stations that would take in the dust from the comet and analyze it. There is a magnetometer on board of the lander, which is, of course, is important for the magnetic field measurements around the comet, but it was also very interesting and important to analyze the attitude of the lander by combining the magnetometer data from the lander and the orbiter. We could actually determine which attitude the lander had as it was on the comet. Then there is the CONSERT instrument that works together with the lander and the orbiter, sending radio signals through the comet to investigate the interior of the comet. Also on the lander there is a drill to drill into the comet. Also there is an instrument to feel how hard is the surface of the comet. Here I give an overview of the journey of the Rosetta spacecraft from 2004, the launch, until 2014, the arrival. So the voyage consisted of 3 Earth flybys and 1 Mars gravity assist. So every time we make a swing by, we get an extra gravity shot from the planet in order to go further out into the solar system. And in this way we were put on a trajectory to the comet. At the deepest point in deep space we had to go to a hibernation mode, of which we would wake up in January 2014 to start really getting closer and closer to the comet. When the spacecraft woke up from hibernation in January, the first thing we did is check out all the subsystems, then all the instruments, and we found the spacecraft in a very good health. And we started already to image in the direction of the comet. And in March 2014 we had the first real observations of the comet, which was at that time still a very small object in the sky, and we were still thousands of kilometers away from the comet, but we were closing in very quickly. Of course there were already educated guesses for the shape based on ground-based observations that were done in the previous perihelion passes of the comet. There was a model made based on this, and very important, the rotation rate was already determined to be about 12 hours, which was a very important indicator. Of course we still had to find out in which direction and how the rotation would be exactly, but of course mainly we wanted to know the shape and look for the landing sites. So then when we got closer in the middle of July, we started for the first time to see the actual shape of the comet. And we could see that this comet did not look like one object. It actually looked like 2 objects glued together. And clearly this looked quite spectacular, but already showed that it was not going to be easy to land on this object. Then when we got even closer, in the beginning of August, we could also really see the surface of the comet, and we could see that the surface was not a smooth surface, and therefore was a very difficult surface to find a good landing position. Nevertheless, a landing site had to be found quickly, and landing sites had to be selected. The Rosetta spacecraft also went along into modern times, in the times of Facebook and making selfies, and the Rosetta spacecraft could make a selfie of itself using the cameras of the lander, looking along the solar panel with the comet in the background, which gave us a very spectacular image in October 2014. Some vital statistics about the comet. As mentioned, the rotation period was in the order of 12.5 hours. So that was close to what was predicted. We found that the comet rotates very nicely around its axis without much nutation. So it's a very clean rotation around its spin axis. The size of the comet is difficult to say because of the irregular shape, but the widest part is about 4 kilometers, the larger part of the comet, and the head is about 2.5 kilometers wide. In order to show the size more clearly with respect to a city on Earth, there's a picture which shows the comet together with a city with skyscrapers to get a feeling for the size. There's another picture showing the comet in the sea in front of a small city, which actually shows also that the comet would float on water